Hello, everybody. We are going to talk about the off-policy actor-critic algorithms. We are group 7 from CS 5446, and I am Liu Qiaofeng, a master student in SOC, and my teammates are Pei Junjie and Xu Zihai. So what is an actor-critic algorithm? Actor-critic algorithm is developed from the general policy gradient algorithms. It learns the value function, which is the critic, in addition to the policy, the actor. So these reduce the gradient variation of the general policy gradient, and it can also make it possible to converge faster than the general versions. The off-policy learning algorithms learn from actions following the policies. These policies are often different from the target one, and is called behavior policy. Note that the off-policy learning algorithm can even learn without following any policies. These give much better sample efficiency and can bring better exploration than the on-policy learning algorithms. So how about just combine them together? So this is what interests us most. In this part, we are going to talk about 3 algorithms. The first one is the vanilla version of the off-policy actor-critic algorithm. The second one is the deterministic policy gradient. And the last one is the deep version of the deterministic policy gradient. We start by introducing the vanilla version of the off-policy actor-critic algorithm, which is off-pack. The off-pack optimizes the objective function showing in the first line. And we can further derive the formula into the following steps. So we can see in the third step, we just ignore the gradient of Q function. This still works, and it can proven that this can simplify the computation of the gradient and is proven to converge. And we can see in the last step that we finally obtain the action value function, but we are using the critic to evaluate the value function. The critic learns the state value function, so we need to do additional things to modify this Q function to the things we want, which is the state value function. So we can just do a subtracting baseline function trick. We can see that we just subtract the V function, and we can approximate these subtraction with the TD error. So we just figure out how to update the actor now. And so now we can just do the update. For the actor, we update the policy by updating the policy parameter theta following the above gradient. We use the important sampling to sample observed data. And for the critic, we just update the state value function. We update the value function parameter omega following the basic TD learning rule. But however, according to Hamid, the original paper didn't take into account the implicit connection of the policy parameter theta and the value function parameter omega. This results in the update direction of the actor does not follow the true gradient direction. And the proof of the convergence property in the original paper is also questionable. But luckily, these problems can be fixed by simply reforming the gradient computation and updating everything using eligibility trace. Note that the basic idea is similar. Now, I will briefly introduce the eligibility trace. Eligibility trace is a temporal record of the occurrence of an event, such as the visiting of a state or the taking of an action. The trace marks the memory parameters associated with the event as eligible for undergoing learning changes. So this is why it is called eligibility trace. And the eligibility trace in this case are denoted as z theta and z omega. So we can see that the updating rule of z theta and z omega is as follows. Note that the gamma and the I here are the parameters, and the theta and omega can finally be updated as below. But note that the update rule here is not the final version, because we need to manage to resolve the conversion issue. So we need to introduce a parameter f for the convergence and for efficiency. So finally, this is what our vanilla version of policy actor-critic algorithm looks like. In each step, we just select an action A in current state S following the behavior distribution pi B, and we can execute this action and get a revert R and next state S pi. Next, we just compute the TD error, and we can also compute the sample importance. Later, we just update the critic and the actor by using the mentioned rules and also the eligibility trace to ensure a stable and to ensure the convergence properties. So next, I will hand over to Zihan to introduce the deterministic quality gradient.
Yeah, thanks, Xiaofeng. And my name is Zihan, and I'm also a full-time master student in SOC. So today I'm going to introduce this paper, Deterministic Policy Gradient Algorithms. So previously in stochastic cases, policy parameters converge to a very good strategy, but there are many issues with the gradient computation. So the first issue is the gradient changes more rapidly when it's near the local optimals, and besides, the gradient is very hard and expensive to compute, and is sometimes even intractable. So in an effort to alleviate these issues, this paper introduces deterministic policy gradient algorithms. So the algorithm is divided into 3 sub-algorithms. And the first is an on-policy deterministic actor-critic, and the following are off-policy deterministic actor-critic, and finally, compatible function approximation. So note that deterministic policy gradient is a special case of stochastic policy gradient. So for the on-policy deterministic actor-critic, the critic estimates the action value function, and the actor assigns the gradient of the action value function. And for off-policy deterministic actor-critic, it simply use arbitrary stochastic behavior policy to generate some trajectories, and then we just learn the deterministic target policy by averaging over the state distribution of the stochastic behavior policy. So finally, compatible function approximation. The original Q function in the deterministic policy gradient will not necessarily follow the true gradient. So in order to solve the issue, we find compatible function approximators such as the true gradient is preserved. Okay. So this is experiments that they performed in the paper. So there are actually 3 experiments, and all of them are conducted under contiguous action variants of the standard reinforcement learning benchmarks. And we only focus on the blue and the red dots. The blue is stochastic off-policy actor-critic, and the red is for deterministic off-policy actor-critic. So generally, as we can see from the graph, compared with the stochastic policy, the deterministic policy gets higher amount of rewards, and also it converges faster and with more stability. So next, I will hand over to Junjie.
Hi everyone, I'm Junjie. My name is Junjie. I'm also a master student in SOC, and this is my last semester in SOC. Today I'm gonna present the paper called Deep Deterministic Policy Gradient Algorithms. This paper was based on the previous paper, DPG. It's a deep version of the DPG is proposed. The author adds some very clever tricks to DPG, and those tricks, there's two tricks are abstract from the deep Q network algorithms, which is also from 2015. And one of them is the network is trained off policy with sample from replay buffer to minimize the correlation of the samples. And the other feature was the network is trained with a target Q network to give the consistent target during temporary difference backups, which is be able to overcome the stability and robustness issue of the DPG. The author also implement the other several tricks to the paper to the algorithms. One is called batch normalization, which is quite normal now to use, but at the 2015 it's also a quite new feature to implement. And another was adding noise sample from the noise process to actor policy, which is be able to dealing with exploration problems in continuous action space. Here is a whole algorithms. It's quite straightforward, and the key part is one is the select action AT. That part was the noise sampling part, and the other part is set 1i equal to ri plus something. That is the target network part, and the last part for the last two lines for the algorithm is update of the target network part. Here's the evaluation from DPG with DDPG by the author in the paper. The author tried several different difficulty level experiment games to test the performance. And from this picture, we can see the light gray line is the original DPG algorithms, and the others was mostly was always implement of target network and also some other features. We can see in most of the game, almost 9 of 10 games, it's deep DPG was performance better, much better than DPG, and so the author gives the summary is that the target network are the key features to improvement. Here we reach the conclusion part. The three algorithms are typical work of policy actor-critical algorithms. The vanilla of policy actor-critic algorithms off-pack, we can see, learn as stochastic policy, and is the first proposed algorithms combining actor-critic and off-policy learning. The deterministic policy gradient algorithms learn a deterministic policy to get a higher efficiency, and the deep version of DPG algorithms learn combine the tricks from deep network and the Q function, which is applicable to more complex problems. That would be all for us. Thank you.